Hello, today we are going to start a new chapter which is turbulent flow. Firstly, let's just understand what do we mean by turbulent flow. This is my pipe in which turbulent flow is taking place. Turbulent flow means my fluid particles will be moving in a zigzag way. Like as I had told you, in laminar flow, the fluid particles were moving along a streamline and those streamlines were parallel to each other. सेम वे यहाँ पे क्या हो रहा है कि जो फ्लूइड पार्टिकल्स है वो एक जिगजैग वे में मूव कर रहा है और जब पार्टिकल्स ऐसे जिगजैग वे में मूव करेंगे तो क्या होगा, एडीज फॉर्मेशन विल टेक प्लेस एंड बिकॉज ऑफ दिस एडीज फॉर्मेशन बहुत ज़्यादा एनर्जी लॉस भी होगा. So in turbulent flow, the fluid particles are moving in a zigzag way. Zigzag way में move करने की वजह से eddies formation will take place. And because of eddies formation, there is high energy loss. Turbulent flow जो है वो large diameter pipes में occur होगा जहाँ पे fluid की velocity बहुत ज़्यादा है. That is, it will occur in large diameter pipes having fluid with high velocity. And if I talk about the Reynolds number, which is R is equal to rho Vd by mu, then for turbulent flow, Reynolds number will be greater than 4000. The next thing that we are going to see is expression for coefficient of friction in terms of shear stress. Here I have considered this uniform horizontal pipe which is having steady flow, and we have considered these two sections, section 1-1 and section 2-2. Now P1 pressure intensity at section 1-1, V1 is the velocity of flow at section 1-1, then L is the length of pipe between section 1-1 and 2-2, D is the diameter of the pipe, F dash is the frictional resistance per unit wetted area per unit velocity, and HF, which is the loss of head due to friction. And as I have shown here, P1 is acting on my section 1-1, P2, that is the pressure intensity at section 2-2, which will act in opposite direction, and F1, which is my frictional resistance. Now if I talk about the forces that are acting here, then they are P1A, P2A and F1. P1A minus P2A minus F1 is equal to 0. Now this F1 is the force due to shear stress. So P1 minus P2 into A is equal to F1, and the force due to shear stress, that is, it will be tau naught into area, and my wetted area is 2 pi RL, or we can say pi dl. So P1 minus P2 into A, now this area which is pi by 4 d square, as this is pipe which means circle and area of circle which is pi by 4 d square. So P1 minus P2 is equal to 4 tau naught L upon D. Then we also know the Darcy-Weisbach equation, which is HF is equal to 4FLV square upon 2GD. And here we'll just divide this both the sides by rho g, so that P1 minus P2 by rho g is equal to HF, and HF will be equal to 4 tau naught L upon rho GD. Then as I said that HF is equal to 4FLV square by 2GD, we'll just compare that. Here on comparing, we'll get tau naught is equal to F rho V square by 2, or if I write it in terms of F, then it will be 2 tau naught by rho V square. This F is my coefficient of friction in terms of shear stress, and if my coefficient of friction is 2 tau naught by rho V square, then my friction factor will be equal to 4 into F, as I have already taught you. So it will be F dash is equal to 8 tau naught by rho v square. The next thing that we are going to study is shear stress in turbulent flow. We know that for viscous flow, the shear stress is given by Newton's law of viscosity. That is, we write it as tau v is equal to mu du by dy. Tau v is the shear stress due to viscosity. And many scientists have worked to find the equation for shear stress due to turbulent flow. The first one was J. Boussinesq. Tau t is equal to eta du bar by dy. Now what is this u bar? Then here I have just drawn in this figure, and suppose I'm showing this distance as y from the boundary, then u bar is my average velocity at a distance y from the boundary. Then tau t is my shear stress due to turbulence, and eta, which is my eddy viscosity. And also we have the ratio of eddy viscosity and mass density, which is known as kinematic eddy viscosity. Like in the case of viscous flow, we had seen that nu is equal to mu by rho, that is kinematic viscosity is equal to dynamic viscosity upon density. Same way यहाँ पे क्या है, kinematic eddy viscosity is equal to eddy viscosity divided by mass density. So this epsilon, that is my kinematic eddy viscosity. और अब अगर मुझे टोटल shear stress के लिए इक्वेशन लिखना है, तो then I'll consider the shear stress due to viscous flow and due to turbulent flow. So it will be tau v plus tau t, which is mu du by dy plus eta du bar by dy. जब laminar flow होगा तब मेरा eta हो जाएगा 0. So my equation that will remain will be tau is equal to mu du by dy. ये जो इक्वेशन दिया है वो जे बूजेनेक ने दिया था, बट इसकी कुछ लिमिटेशन पता चली थी, विच वॉज दैट ईटा कांट बी प्रेडिक्टेड. जो एडी विस्कोसिटी थी वो प्रेडिक्ट करना काफ़ी मुश्किल था. इस वजह से इस इक्वेशन का बहुत ही लिमिटेड यूज़ हो गया. फिर एक और इक्वेशन फाइंड किया दूसरे साइंटिस्ट ने, हु वॉज रेनॉल्ड्स. सो उस इक्वेशन को बोला रेनॉल्ड्स एक्सप्रेशन फॉर टर्बुलेंट शेयर स्ट्रेस. रेनॉल्ड्स जी ने सोचा कि ये जो मेरे फ्लूइड पार्टिकल्स हैं वो एक zigzag वे में मूव करते हैं, दैट इज़ वाई वी आर हैविंग फ्लक्चुएटिंग वेलोसिटी इन x एंड y डायरेक्शन. और इसी फ्लक्चुएटिंग वेलोसिटी को उन्होंने बोल दिया कि फ्लक्चुएटिंग कंपोनेंट ऑफ वेलोसिटी अगर x डायरेक्शन में है तो इट इज़ u डैश, और अगर फ्लक्चुएटिंग कंपोनेंट ऑफ वेलोसिटी y डायरेक्शन में है टर्बुलेंस की वजह से तो वो हो जाएगा v डैश. और ये दोनों जो मेरे फ्लक्चुएटिंग कंपोनेंट्स हैं दैट इज़ u डैश एंड v डैश, वो टाइम के साथ वेरी होंगे. इस वजह से उन्होंने जो इक्वेशन दिया वो था टाउ बार इज इक्वल टू रॉ u डैश v डैश बार. And this equation we call it as Reynolds stress. Tau bar is equal to rho u dash v dash bar. But this equation also had its limitation, because of which another scientist had done some work. His name was L. Prandtl. उनकी जो theory है it's popularly known as Prandtl mixing length theory for turbulent shear stress. इस इक्वेशन का क्या लिमिटेशन था, तो u डैश v डैश अगर हमें पता होंगे, if we are able to calculate u dash v dash, then only we'll be able to find the turbulent shear stress. But it's very much difficult to find this u dash v dash bar, and this was the limitation of the Reynolds stress. और इस डिफ़िकल्टी को ओवरकम करने के लिए एल प्लांडल ने हमें एक मिक्सिंग लेंथ हाइपोथेसिस दिया है जिसको यूज़ करके हम टर्बुलेंट shear स्ट्रेस फाइंड कर सकते हैं. Here as you can see this, I'm indicating some cross marks. ये है मेरे fluid particles. Suppose जो मेरे fluid particles है वो एक लेयर में से दूसरी लेयर में जा रहे हैं और दूसरी लेयर में जाके वो इस तरह से मिक्स हो जाते हैं कि उनकी जो मोमेंटम है उन पार्टिकल्स की इन द एक्स डायरेक्शन वो क्या हो जाती है, वो सेम हो जाती है. अगेन आई विल से that my lump of fluid particles are moving from one layer to the other layer, and the fluid particles are mixed in the other layer in such a way that the momentum of the particles in the x direction is same. Then this distance between two layers in the transverse direction, that we call it as the mixing length. मतलब ये जो डिस्टेंस हो गया मेरी दो लेयर्स के बीच में ट्रांसवर्स डायरेक्शन में, वो क्या हो जाता है, वो है मेरी मिक्सिंग लेंथ. दिस वाज द मिक्सिंग लेंथ हाइपोथेसिस गिवन बाय प्रांडल. एक लेयर में से मेरा पार्टिकल जो है वो दूसरी लेयर में जा रहा है और दूसरी लेयर में जाके वो इस तरीके से मिक्स हो रहा है कि जो मोमेंटम है पार्टिकल्स की इन एक्स डायरेक्शन वो सेम हो जाती है. Then Prandtl had assumed that the velocity fluctuation in the x direction, which is u dash, it is related to mixing length like this. U dash is equal to L du by dy. और जो v dash है, that is the fluctuation component of velocity in the y direction, it is related to mixing length like this. V dash is equal to L du by dy. Then we can say that u dash v dash bar जो हो गया वो क्या हो जाएगा अब एल डी यू बाई डी वाई इंटू एल डी यू बाई डी वाई. तो ये हो जाएगा एल स्क्वेयर इंटू डी यू बाई डी वाई होल स्क्वेयर. देन वी कैन राइट द shear stress in turbulent flow like this. Tau bar is equal to rho L square du by dy whole square. Here in this diagram I am trying to show you कि ये जो मेरी पाइप बाउंड्री है उसके एकदम नज़दीक में there will be viscous shear stress, but except near the boundary viscous shear stress जो हो जाएगा वो होगा मेरा negligible. Why? Because the shear stress due to turbulence will dominate. So except near the boundary my viscous shear stress is negligible, and we can write the total shear stress at any point in turbulent flow using this equation. Tau bar is equal to mu du by dy plus rho L square du by dy whole square. इसमें जैसे I explained that near the boundary viscous shear stress will be present, but except near the boundary viscous shear stress will be negligible. Next we are going to derive velocity distribution equation for turbulent flow in pipes. Now here we already know the equation for total shear stress at any point, which is tau bar is equal to mu du by dy plus rho L square du by dy whole square. But as I was emphasizing the point that viscous shear stress is negligible except near the boundary, so it was assumed that the shear stress in turbulent flow is given by the equation tau bar is equal to rho L square du by dy whole square. और ये जो इक्वेशन है उससे हमें वेलोसिटी डिस्ट्रीब्यूशन कब मिलेगा, जब हमें मिक्सिंग लेंथ और y के बीच का कोई रिलेशन पता हो. फॉर दैट प्रांडल हैड अज्यूम्ड कि जो मिक्सिंग लेंथ है मेरी इट इज़ अ लीनियर फंक्शन ऑफ द डिस्टेंस y फ्रॉम द पाइप वॉल. लीनियर फंक्शन है, so how can I write it? L is directly proportional to y, विच इज़ L इज़ इक्वल टू KY, और K जो है वो एक कांस्टेंट है विच इज़ नोन एज कारमन कांस्टेंट, and its value is 0.4. So now let's just write the equation for shear stress, which is tau bar is equal to rho L square du by dy whole square, and we'll just replace this L by ky, so it will be rho into ky whole square into du by dy whole square. Now this du by dy whole square is equal to tau bar upon rho ky square. Therefore we can write that du by dy is equal to under root of tau bar by rho into 1 upon ky. This tau bar we can also write it as tau. अभी जब हम लोग shear stress को पाइप बाउंड्री के नज़दीक में कंसिडर करेंगे, तब मेरी जो y की वैल्यूज़ है, those values will be small near the pipe boundary. Therefore, Prandtl had assumed that the shear stress will be constant and it will be denoted by tau naught. So du by dy is equal to 1 upon ky under root of tau naught by rho. Now this tau naught is shear stress and its dimensions are m1, L minus 1, T minus 2, and for rho we have m L minus 3. Taking this in under root, so it will be L square upon T square, and square root of that will be L by T, which is under root of tau naught by rho is having its unit same as velocity, which is meter per second or centimeter per second, and so it was given a name which is shear velocity, and it was denoted by a symbol U star. So we can write this du by dy is equal to 1 upon ky into U star, because U star is equal to under root of tau naught by rho, and U star is known as the shear velocity. Next thing we are doing is we are integrating this equation. So we get du by dy, it will become U, 1 upon k will be constant, U star is also a constant, and 1 upon y will be log y to the base e, or we can say ln y, plus a constant will come because we have performed integration. Here, as per this equation, velocity is varying with logarithm of the distance from the boundary, or we can say that velocity distribution in turbulent flow is logarithmic. And when we were deriving viscous flow through circular pipe, there we had seen boundary condition, which was at y is equal to r, we'll have maximum velocity, that is u is equal to u max. Here we'll just use that. So u max is equal to u star by k, y will be replaced by r, log r to the base e plus c. Writing it in terms of c, we get u max minus u star by k log r to the base e. This is my first equation, and here putting the value of c, we'll get u is equal to u star by k log y to the base e plus u max minus u star by k log r to the base e. Then we can write this as, taking u star by k as common, in the bracket we'll have log y minus log r. Subtraction will become division, so it will be log y by r to the base e plus u max. Then we also know the value of our Kármán constant, which is 0.4. We'll place that, so u is equal to u max plus u star by 0.4 log y by r to the base e. So we get u is equal to u max plus 1 upon 0.4 is 2.5. So 2.5 into u star into log y by r to the base e. This equation that we have derived, that we call it as the Prandtl's universal velocity distribution equation for turbulent flow in pipes. U is equal to u max plus 2.5 u star log y by r to the base e. You'll have to remember this in order to solve the examples. Now I'm just taking this u max minus u is equal to minus 2.5 u star log y by r to the base e. Also, I'm changing log to the base e to log to the base 10. And when this minus will get multiplied in the bracket, then it will become log r by y to the base e. Now log r by y to the base e is equal to 2.3 log r by y to the base 10. So u max minus u by u star is equal to 2.5 into 2.3, which is 5.75 log r by y to the base 10. This u max minus u upon u star is equal to 5.75 log r by y to the base 10, where this u max minus u is known as velocity defect, which is the difference between the maximum velocity and the local velocity, and we call it as velocity defect. In this video, we understood what is turbulent flow, then we derived the expression for coefficient of friction in terms of shear stress, then we saw shear stress in turbulent flow given by J. Boussinesq, then Reynolds, and then Prandtl. And we also derived the velocity distribution equation for turbulent flow in pipes, which is u is equal to u max plus 2.5 u star log y by r to the base e. And also we saw that the difference between maximum velocity and local velocity is known as velocity defect. Thank you.